Welcome to the section on fitting classifiers by empirical risk minimization. This section is very much parallel to our earlier section on regression via empirical risk minimization. We have to really discuss two things in order to do classification. And the first is, how do you embed categorical variables V? So we have script V. It's a finite set of possible values of classes that our target variable V can take. And we want to take the target variable V and embed it into a vector Y in Rm. And we're going to let Y be psi of V. And of course, psi of V only takes k values as well, because V only takes k values. And so we have we have capital K vectors, psi1 through psi capital K. Each of those are the images under the map psi of the classes V1 through Vk. And we call these vectors psi I the representative of Vi. And the set of all representatives, psi1 through psi k, is called the constellation of representatives. Some examples, we might embed true to 1 and false to -1. We might embed true to 1 and false to 0. Those are mappings from a two-element set of categories into the real numbers. We might also map the three-element set, yes, maybe, no, to the real numbers 1, 0, and -1. Another thing we might do is do a one-hot embedding, where we have, say, three categories: apple, orange, and banana. And we map apple to E1, orange to E2, and banana to E3, where E1 and E2 and E3 are the canonical unit variables, unit vectors in R3. Now, we might also take three categories and map them directly to the reals. If we've got, say, three horses, horse 3, horse 1, and horse 2, we might map them just to 3, 1, and 2. Well, we might do really complicated things like word to vec, which maps a large number of words to vectors in R300. So the one-hot embedding takes k classes and maps into Rk. So psi of Vi is just Ei. We can do it to Booleans if we have Booleans where the first representative maps to 1, 0, and the second representative maps to 0, 1. There's another version of the one-hot embedding called the reduced one-hot embedding, which maps one of the classes to 0, and the other k-1 classes map to the unit vectors in Rk-1. If we had Booleans, in that case, that reduces the mapping from the one-hot embedding. It maps the Booleans to 1, 0, and 0, 1, and the reduced one-hot embedding would map the Booleans to 0 and 1, a one-dimensional embedding rather than a two-dimensional embedding. We might also have yes, maybe, no, and the default be maybe, in which case that's three categories. We would map it to R2 via the one-hot embedding, the reduced one-hot embedding, and we put maybe as the default, so maybe would map to the origin, yes might map to 1, 0, and no might map to 0, 1. Now, once we've embedded, we are going to have to do something we didn't have to do in regression, and that is unembed. And in particular, we've got to unembed points which are not mapped to by our embedding map. And so we will see how to do that. Let's look at how this works from the overall predictor point of view. So we start off, we embed our raw input u to a feature vector x via the map phi. The feature vector x lives in Rd. And we've got a raw output, which is in our data set, which is a v, which is a categorical. We map it to psi of v, which is y, which lives in Rm. We use these data points. We've gone from n ui vi pairs to n xi yi pairs, and we use those to create a predictor g, which maps Rd to Rm. And for any x, it will give us a y hat, which lives in Rm. And now what are we going to do with y hat? Well, what we hope is that if y hat is g of x, then y is somehow close to psi of v, where v is one of the categories. And close here would usually mean in the norm. So I've got the norm of y hat minus psi of v is small for one of the v's. And to get the prediction, we've got to unembed, we've got to pick a v hat, which is corresponding to the y hat. And we're going to define a map psi dagger, which takes vectors in Rm and maps them back into the target set script v, the un-embedding function. So once we've got a psi dagger, well, we can use it in order to construct our final classifier. Our final classifier has to take a u and give us back a v hat. And the way it's going to work is we're going to take u, pump it through our embedding phi to give us an x, pump that through g to give us a prediction y hat, and then pump that through the unembedder psi dagger to give us a v hat. And then we'll call that map from u to v hat, capital G. G is the composition of psi dagger with g with phi. In other words, we embed, we predict, and we unembed. The usual unembedding that people choose is the nearest neighbor unembedding. And what it does is it says, well, you've got a y hat, pick out of all the categories in script v, the one such that psi of v is the closest to y hat. So minimize over all little v's in script v the norm of y hat minus psi of v. And that is called psi dagger of y hat. And if it so happens that there are two vectors v, two classes, for which their embedded points are equally close to y hat, well, then you can break ties any way you want to. Another way to say it is what we're doing is we're choosing the target variable, the target category, which is associated with the nearest representative to y hat. So here's the simplest possible example. If we've embedded the booleans true and false to 1 and minus 1, so those are our representatives psi 1 and psi 2, well, then we would unembed by mapping any positive number y hat to true and any negative number y hat to false. Because if we've got two representatives, which we have, minus 1 and 1, well, if y hat is positive, then the closest representative is 1, and if y hat is negative, then the closest representative is minus 1. Suppose we've got one hot. So let's look at the R2 case. So here we have y1, y2, two components of y. We have 1, 0 and 0, 1. This will be psi1 and this will be psi2. Those are the embeddings of our two categories in the case of the Booleans. So this would be psi of true and this would be psi of false. And then we develop a predictor, and that predictor gives us back a y hat, which is anywhere in the two-dimensional planes. And then what do we do? Well, we'll say if you're on this side of the plane, if y hat's over there, then corresponding v hat will be psi1, and if you're on this side of the plane, then the corresponding v hat will be psi2. And to be precise, there will be not psi1 and psi2, but v1 and v2, the corresponding targets, true and false. And so here it's clear. All you do is you look at the two components of y hat 1 and y hat 2. And if y hat 1 is larger, then you're on this side of the plane. You're on this side of the plane. And if y2 is larger, well then you're on this side of the boundary between the two, which separates the region which belongs to psi1 and the region that belongs to psi2. Let's put it another way. If y hat 1 is greater than y hat 2, then the arg min over v of the norm of psi v minus y hat is v1. Otherwise it's v2. This is true more generally. If we want to find out what is the solution in general to this problem of un-embedding, what is psi dagger when we've used the one-hot embedding, it turns out that this is exactly what we think it is. We look at the largest component of the vector y hat and we return the corresponding target vector. So if y hat 3 is the largest component of y hat, then our un-embedding psi dagger would return v3. And the reason for that, we can just work out algebraically what it is. If I look at what y hat minus EI is, well, that's the 2 norm squared of that quantity is the 2 norm of y hat plus 1 minus 2 y hat transpose EI. And y hat transpose EI is just y hat I. It's just the ith component of y hat. And so picking I to minimize that quantity is precisely the same as picking I to maximize y hat I. Suppose we've embedded the reduced one-hot embedding. We've used the reduced one-hot embedding to embed yes, maybe, no as 1, 0, 0, 0, or 0, 1. Well, then we unembed in exactly the same way. For any point y hat in the R2 plane, we pick the closest representative, and that tells us which target variable we're predicting. So if y hat is over here in this region, it's I'm going to return yes. Yes is psi dagger of any point in that region. No is psi dagger of any point in this region. And maybe is psi dagger of any point in the remaining region. And that's nicely expressed in the little cases construction there. And again, you can choose any value you like on the boundary. So more generally, we might have an embedding of categories into Rm, and that gives us a whole bunch of different representatives, here represented by these blue dots. And for any given point y hat in Rm, we want to find the closest representative. And the way we do that is via the Voronoi diagram that we saw earlier. And so in particular, this region right here is the set of points for which the closest blue dot is that one in the middle. And so that means that if y hat is in that region, I will return the corresponding representative to that blue dot right there. And as we've seen when we looked at the nearest neighbor classifier, the regions which correspond to each target variable or to each representative are polyhedra. Now suppose we're using a parametrized predictor, so g is a function of a parameter theta, and g is might be theta transpose times x if it's a linear predictor, or it might be something more complicated. Well, then theta is the parameter we choose, and then once we've got a predictor g theta, we compose it with the embedding psi and the un-embedding, this should be the embedding phi. Let's just see that we use that same notation here. That should be phi. So this should say psi dagger g theta phi of u, not psi of u. And that's the classifier that gives us v hat. So what do? We choose theta using ERM in a training data set. And we validate the predictor by looking at the performance metric, which might be the error rate, on a test data set. Of course, the performance metric might be the Neyman Pearson error measure as well. And so when we're doing parameterized predictors for classification, we might use a tree-based predictor. And that's got a name, it's very commonly used, it's called a classification tree. And then theta encodes the tree, tells us when to split at each node and the threshold and leaf values. And each leaf has a corresponding value of y hat, and that leads immediately to a corresponding target because we can un-embed the y hat to the v hat. And we might use a neural network, in which case theta gives us the bias or the offset and the weights in the different layers, and then y hat is the output of the last layer, and again we un-embed. We might use a linear predictor. Theta is a d by m matrix, and y hat is just theta transpose times x. Now, the other major piece that we need for classification is a loss function. And it turns out that the loss function that we would use for classification is slightly different from the typical loss function we would use for regression. And we're going to see in the next section several different loss functions for classifiers. For the moment, I want to consider the simplest loss function. That's for example, the square loss. Now the way it works is just like it did in regression is that we have a loss function. This is not quite right. It should be the loss function maps Rm cross Rm to R. It's a function of y hat and y. And it tells us how much prediction y hat bothers us when the true observed value of y is what it is. And it's going to be, of course, one of the representatives. Those are the only possible values for y, because the only possible values for v are v1 through vk, and when we embed those, we get psi1 through psi k. As a result, we can think about loss functions slightly differently. Rather than thinking about a loss function as taking a y hat and a y, we can say, well, really what we have is we have k different loss functions. The first one is the loss function, which tells us how much loss y hat causes us when the target variable is v1. That's L of y hat psi1. Or when the target variable is v2, then we get a different loss, and we'll think of that as a totally different loss function. And we might even use this kind of notation, L sub j of y hat, to say, well, actually, we've got a different loss function for j is 1 up to capital K. And this loss function only depends on y hat, because the dependency on y is taken care of by j. What it is it's how much we dislike predicting y hat in the particular case where the target variable is vj, or correspondingly when y is psi j. And typically what you want is that the loss function L of y hat psi j is a non-negative number, and it's small when y hat is close to psi j. So very commonly we might use the square loss, which is the 2 norm of y hat minus psi j. We'll see other loss functions which work much better for classification in the next section. So how do we think about two different loss functions when we're using the square loss in the Boolean case? Well, they're translated versions of the quadratic function. This is, on the right here, is L of y hat y when y is psi 2, and psi 2 is just 1. And this is L on the left here of y hat and y when y is psi 1, which is just minus 1. And we can see that the one on the right is a quadratic centered at 1, and the one on the left is a quadratic centered at minus 1. So we're given a training data set, xi, yi pairs, for i's 1 up to n, and we've got a parameterized predictor, g theta. And empirical risk minimization simply says, well, what we do is we minimize the average loss function over theta, where the loss is evaluated at y hat I and yi. And y hat I is just our prediction evaluated at xi. So ERM chooses the theta to minimize the loss. Regularized ERM chooses the theta to minimize the empirical risk plus lambda times the regularization function. And lambda here is a positive regularization hyperparameter. And in most cases, we're going to need to do numerical optimization to find theta. There won't be an explicit formula. In the least squares case, it's quite interesting. Let's consider what that is in the Boolean case. So in the Boolean case, let's have u be one-dimensional, just to make it easy for me to draw. And let's have v be either true or false, and we'll embed true to 1. So this will be psi of true, and this will be psi of false. And at each of our data points will give us a value of u and a corresponding value of v, which will embed to give us a 1 or a minus 1. So we might have a bunch of data points here and a bunch of data points here, and that's our data points. And then what we're going to do is we're going to fit that with least squares. So we're going to say use linear predictor, y hat is theta transpose x, and that will fit a straight line right there. Now, because we're un-embedding using psi dagger here, remember, is the inverse, is the un-embedding map corresponding to the one-hot embedding. And so it's going to say, well, whenever y hat is positive, your prediction should be true, and whenever y hat is negative, your prediction should be false. And if our line, the plot of our predictor theta transpose x happens to be like this, that means that whenever u is over to the right here, I predict true, and whenever u is over to the left here, I predict false. And if we look at our data, we can see, well, that in my simple sketch there didn't seem to do too badly. Although it's an astonishing idea that we can fit a function that only takes values 1 and minus 1 with a straight line. This is called a least squares classifier. We're using a square loss, we might be using a square regularizer, and we just solve the RERM problem, and this is the case where we can solve it exactly using least squares. Here's an example in 2 dimensions, and we see that it kind of works. Right, so here I've got u is in R2, it's embedded in R3 as 1, u1, u2, remember we've got the constant feature, and we've embedded minus 1, 1 just directly as y is minus 1 or y is 1 as our 2 representatives. Psi 1 is minus 1, psi 2 is 1. And we use a square loss and a square regularizer, and these are our predictor. This is our predictor. The shading here shows which points u1, u2 map to 1 and which points map to minus 1. And of course, really what's going on is that this here, this boundary, that's the boundary where y hat is 0, and y hat is a linear function of u1, u2. Y hat, we know what it must look like. Y hat must be equal to theta 1 plus theta 2 u1 plus theta 3 u2. And this line right here is the u1s and u2s, which result in y hat being 0. Over on this side we have y hat positive, and over on this side we have y hat negative, and our un-embedding maps that to 1 and minus 1 to give us a classifier. Now if we have the Neyman Pearson metric, so the Neyman Pearson metric, remember what it is, it says we're going to consider a weighted sum of the different errors, where EJ is the rate of mistaking VJ for some other class. And kappa here is going to be the weight. So kappa J is how much we care about mistaking VJ, about predicting the answer in the case where the true target variable is VJ wrong. And what we do is we scale the losses by kappa. So suppose we have loss functions. We've seen already the square loss, which we'll call L tilde y hat, well then L tilde y hat psi j, for example, might be the square loss. It might be the square of y hat minus psi j, or it might be the norm of y hat minus psi j squared. Well, then we'll construct a loss function from these unweighted losses by taking a weighted combination of these losses. So we'll use a loss function L of y psi j, which is kappa j times L tilde of y and psi j. So let's look at an example. Suppose I've got psi 1 is minus 1 and psi 2 is 1. We're going to care about the Neyman Pearson metric. Now, because this is Boolean, there are two types of errors we can make, the false negatives and the false positives. And our Neyman Pearson metric is going to be kappa times the false negative rate plus the false positive rate. Kappa is some number greater than 0. Notice here that we've only got one scalar kappa, whereas on the previous slide we had the number of scalar kappas equal to number of categories, and so we really should have kappa 1 times EFN plus kappa 2 times EFP. And here, of course, kappa is simply kappa 1 divided by kappa 2, if you like, because I can set one of the kappas to 1, and all that matters is the ratio of the two kappas in terms of affecting which prediction I get. Now, our loss function, we're going to use the square loss, but we're going to scale it. And so we'll use y hat minus y squared when y is minus 1. And we'll use kappa times y hat minus y squared when y is 1. And that will give us a weight which is greater when the true y is 1. And so we want to make sure that we are penalizing here false negatives more than false positives. Here's an example. So square loss, sum of squares regularizer. Now, this on the left here is the ROC curves, and they correspond to minimizing the weighted sum kappa EFN plus EFP. And these are the two losses, the training losses in blue and the test losses in red. On the right-hand plot over here, we see the minimum error classifier, which is given by when kappa is 1. And that would correspond to this point down here. Now, if we pick kappa as 0.4, well then we're very concerned to make sure that we don't mistake any red points for blue points, and we end up with a classifier that has moved the boundary in this direction. Conversely, if we pick kappa is 4, well then we're very concerned to make sure we don't mistake any blue points as red points, and so we move the boundary in this direction. And by varying kappa, we will vary our preference for what type of errors we're willing to tolerate. So let's summarize. A classifier is a predictor when the raw output is categorical. We have categories V1 through Vk. When k is 2, it's called a Boolean classifier. When k is greater than 2, it's called a multi-class classifier. Now we might have various error rates summarized in a confusion matrix. Now, when we're fitting a classifier to training data via ERM or regularized ERM, we embed the raw output V into RM using psi. The vectors psi 1 through psi k are then the embeddings of our targets V1 through Vk. We now use ERM to build a predictor for y. We unembed to get y, Our predictor will give us a y hat, which we can unembed to get a class prediction v hat. We do this via nearest neighbor unembedding. Next section we will talk about special loss functions for classifiers.